So sinusoids form the basis for most of the signals that we're going to encounter in all of this stuff. And I want to just show you a lot of different ways that you can express a sinusoid. I mean, the simplest way is you've got some x of t, and we can express it as, for example, a, some real number, times the cosine, for example, of omega t with a phase shift. And of course, omega is the radian frequency, 2 pi times the frequency in hertz. We're assuming time variable. These two constants are amplitude and phase of this. And of course, if omega, so let's just remind ourselves of a couple of things. So omega t you can think of as being units of radians. It's a pure number, but it's radians. And so if that's the case, omega has units, it's like 2 pi times the frequency, where the frequency is 1 over the period, and the time is in seconds, and the frequency is in hertz, inverse time. And this thing then is in units of radians per second, right? And so we can talk about it elsewhere and talk about the relationship to circles and trigonometry and so forth. But what I wanted to go back and do is just look at the different ways that you can express a sinusoid, and especially using complex numbers, this can really simplify things. So let's look at some of the other possibilities. So we could also say x of t equals a. We could express this as a sine function if we want to, but it's going to put a phase shift in here, an additional phase shift, and we could say that's 90 degrees. Okay, so we can operate everything in degrees, or we could represent this as a phase shift of pi over 2 radians, and this one is probably, most of the time, this works better in your calculator. Another way you can represent all this stuff, if you want to, and this involves looking at some trig identities or whatever, but you could express this stuff as some other constant a times the cosine of just omega t without a phase shift, and a b times the sine of the same omega t. And if you represent things that way, then a turns out to be the capital A times the cosine of the phase shift, and the b equals a times the sine of this phase shift. So there's an alternate way of writing this stuff. Actually, I think there's a minus sign according to my notes here. All right, so these are all trigonometric ways of doing this stuff. Other ways that will turn out to be much more convenient. And again, using complex numbers frequently simplifies things quite a lot. So one of the classic tricks that we use, especially in electrical engineering, is to write these things as the real part of a complex number. All right, so it's like the projection on the x-axis. In this case, all these things, if we go back to this first form, this would be the real part of the complex exponential, e to the j times, and now the argument of this thing fits in here, omega t plus v. All right, and so this form and this form are equal, but now we use this complex exponential form. We can multiply this thing out and get yet another form for this that's handy. So we can have e to the j phi times e to the j omega t. All right, so this part is not time varying. All right, and it's just the phase shift. So this is another way of doing it. And finally, the way that we're going to do it that is really the most flexible, and it really benefits what we're doing here, is we're going to group these things together and make this just some complex number z times e to the j omega t. And in some of your classes, you probably learned about phasors, and this is part of the phasor. As long as we know what the frequency is, we can just focus on all the real information about this is z, where, of course, z is just e to the j phi, which has a magnitude part, a real number, times a phase shift. All right? And so this entire number then can be done by this separate way of doing things. This turns out to be a lot more, it may be counterintuitive, but using complex numbers to do this stuff turns out to be a lot easier, and we can work through some examples of that. But this is the form I want to use as we move forward.